Welcome to a journey through one of the most fascinating thought experiments the human mind can contemplate. As you settle in and let your body relax, we're going to explore together what would happen if time itself simply stopped. Not slowed down, not paused like a video, but truly, completely stopped. Let your breathing slow, get comfortable, and let's begin this curious exploration. Imagine, if you will, the very instant that time ceases to flow. In that impossible moment, everything in motion would hang mid-action, suspended in a way that seems almost magical. A bird frozen mid-flight, its wings caught at the precise angle of an upward stroke. A falling leaf suspended between the branch and the ground, never to complete its descent. Water pouring from a faucet would become a crystalline sculpture, each droplet perfectly spherical, hanging in space like glass beads on an invisible string. The Earth itself, spinning at over 1,000 miles per hour at the equator, would hold its position in space. Waves in the ocean would become solid hills and valleys of water. Every car on every highway, every person mid-step, every spinning wheel and turning gear would simply hang there, motionless, waiting for a continuation that would never come. It's a strange and beautiful image when you think about it, this frozen world where motion itself has become a memory. But the consequences would extend far beyond this eerie stillness. You see, you'd be blind almost instantly, and the reason is fascinating. Vision depends on light traveling into your eyes, photons bouncing off objects and entering your pupils to be processed by your retina. But if time has stopped, those photons stop moving too. Light itself would freeze in place, trapped mid-journey between its source and your eye. The last photons to enter your eyes before time stopped would create one final image, and then nothing more would follow. Darkness would descend, not because the lights went out, but because the light itself can no longer reach you. It's a profound kind of blindness, one where the light still exists all around you, shining from the sun and every lamp and screen, but it's paralyzed, unable to complete its journey to let you see. You'd be surrounded by frozen light, invisible curtains of photons suspended in the air, and yet you'd perceive only that last image, fading into permanent darkness. And in that darkness, there would be something even more unsettling. Sound would completely vanish, and the silence would be unlike anything you've ever experienced. Think about the quietest place you've ever been. Maybe a library late at night, or a snow-covered forest, or a soundproof room. There was still sound there, even if just the whisper of your own breathing or the faint ringing in your ears that comes from true quiet. But in a world where time has stopped, there would be nothing. Sound is a wave, a vibration traveling through air molecules, each molecule bumping into the next in a chain reaction that eventually reaches your ear. But frozen time means frozen air molecules. The last sound wave to reach your ear would be the last you'd ever hear. No echo, no whisper, no rustle or hum. Not even the sound of your own heartbeat, because the mechanical movement and the sound it creates would both require time to propagate. It would be a silence so complete, so absolute, that it's almost impossible for our minds to truly grasp it. A silence that doesn't just mean an absence of noise, but an absence of the very possibility of noise. In this frozen world, heat would disappear, and this is where things become truly strange. Heat, you see, is movement at the molecular level. When something is hot, its molecules are vibrating rapidly, bouncing around with tremendous energy. When something is cold, those same molecules are moving more slowly, more sluggishly. But temperature is fundamentally about molecular motion, and without time, there can be no motion. The concept of heat would become meaningless. The sun, burning at millions of degrees, would no longer be hot. The ice in your freezer would no longer be cold. Everything would exist at the same strange state of non-temperature. You wouldn't freeze to death because freezing is a process that requires time. You wouldn't burn because burning requires time. You'd simply exist in a universe where thermal energy has become a frozen snapshot, as still as everything else. It's a peculiar thought that the warmth of the sun and the chill of winter wind would both become neutral, neither hot nor cold, just static arrangements of motionless molecules. And speaking of burning, fire itself would be frozen like a sculpture, and what a sight that would be if you could somehow see it. A candle flame would hang in the air, its characteristic teardrop shape perfectly preserved, the yellow and orange and blue layers visible like a cutaway diagram. But it wouldn't flicker, wouldn't dance, wouldn't consume the wick. Fire is a chemical reaction, combustion, where fuel combines with oxygen and releases energy as heat and light. But chemical reactions require time to proceed. Molecules need to collide, bonds need to break and form, electrons need to shift from one state to another. With time stopped, that roaring fireplace would become a strange sculpture of flame-shaped plasma, caught between one moment of combustion and the next. The wood wouldn't burn away, the heat wouldn't radiate, the light wouldn't shine, for light too requires time to travel. It would be fire that isn't fire anymore, just the physical remnants of a process interrupted at the most fundamental level. And here's where your survival becomes impossible in yet another way. You wouldn't be able to breathe, not even a little bit. Breathing requires so many processes that depend on time. Your diaphragm muscle needs to contract, pulling your lungs open, creating a pressure difference that draws air in. But muscle contraction is a process, and processes require time. Even if somehow your muscles could still move in frozen time, the air itself couldn't flow. Air is made of molecules, nitrogen and oxygen and carbon dioxide, and they need to move from areas of high pressure to low pressure. They need to tumble and flow and drift into your lungs. With time stopped, those air molecules are as frozen as everything else. You couldn't inhale because there's no mechanism for the air to enter. You couldn't exhale because there's no mechanism for it to leave. Your last breath would be truly your last, held forever, neither inhaled nor exhaled, just existing in whatever state it was in when time ceased. The oxygen in your blood couldn't circulate, couldn't diffuse into your cells. But then again, your cells couldn't use that oxygen anyway because cellular respiration is a chemical process, and we've already established that chemistry requires time. Now let's consider something even more fundamental to our existence. Gravity might stop working, and this is a possibility that comes from thinking about what gravity truly is. According to Einstein's general relativity, gravity isn't really a force in the traditional sense. It's a curvature of space-time itself, caused by the presence of mass and energy. Objects don't fall because some invisible force pulls them down. They follow the curved paths through space-time created by massive objects like the Earth. But notice that word, space-time. Space and time are woven together into a single fabric. If time stops, does space-time itself stop functioning? If the flow of time ceases, can the geometry of space-time still guide objects along their paths? It's possible that gravity, like everything else, would simply freeze. The Earth would no longer pull you down. The sun would no longer hold the planets in orbit. But you wouldn't float away because floating is a process that happens over time. You'd just be locked in place, held by nothing, pulled by nothing, existing at whatever point in space you occupied when time stopped. The apple would hang above Newton's head forever, neither falling nor floating, just being. In this impossible scenario, technology would be useless, completely and utterly non-functional. Every device you own, from the simplest mechanical clock to the most sophisticated smartphone, requires processes that unfold over time. Electricity is the flow of electrons through a conductor, but flow requires time. Your phone's processor performs billions of calculations per second, but calculations are sequential processes. Even if electricity could somehow still move, the computer couldn't process anything because processing requires a before and an after, a cause and an effect, and those concepts are meaningless without time. A mechanical watch would stop, its gears frozen mid-tick. A digital clock would display the same numbers forever. Your car wouldn't run because combustion engines require precisely timed explosions of fuel, thousands per minute. Even simple tools would be problematic because using them requires motion, and motion requires time. A frozen world would be a world without technology, where every human innovation that depends on change and process and sequence would become nothing more than a static sculpture. But here's perhaps the most unsettling part of this thought experiment. Your own body would be a paradox, an impossible contradiction. If time has truly stopped for the universe, it must have stopped for you too. Your neurons can't fire because that requires electrical and chemical signals to propagate, and propagation requires time. You can't think because thinking is a process of neurons forming and breaking connections, of neurotransmitters crossing synapses, of patterns forming and dissolving in the vast network of your brain. If you can't think, can you be conscious? Can you be aware that time has stopped? If you were aware, you would be experiencing the passage of subjective time, which means time hasn't really stopped for you, which means you're somehow exempt from this universal freeze, which creates all sorts of logical problems. Perhaps the only consistent answer is that in a world where time has stopped, you can't be conscious of observing it. You would be frozen to your last thought suspended, never completed, never followed by another. Your awareness itself would be a snapshot, a moment of consciousness that can neither progress nor fade, just existing in an eternal now that can't even be called a moment because moments require time to define them. And finally, we arrive at perhaps the most profound realization of all. No process could ever finish or begin. Every event, every change, every transformation requires a sequence. First this happens, then that happens. Cause leads to effect. Beginning leads to middle leads to end. But sequence itself is a concept built on time. Without time, there is no first and second and third. There is no before and after. There is only a single eternal state. That cup falling from the table would never complete its journey to the floor. The shatter would never happen. But it also couldn't be said to be falling because falling is a process, and there are no processes anymore. Every unfinished task would remain unfinished forever, but also couldn't be called unfinished because that implies it might one day be finished. Every story would end mid-sentence, but also would never have begun, because beginning and ending are temporal concepts. The universe would exist in a state of perfect, crystalline stillness, where change itself has become impossible, where the very concept of events has lost all meaning. Nothing ends. Nothing begins. Everything simply is, frozen in an eternal present that can't even be called present because presence is defined in relation to past and future, and those don't exist anymore either. Now, as you continue to relax and let your mind wander through this frozen landscape, let's explore what this world would truly be like. A world where time itself has ceased, where the fundamental fabric of reality has changed in ways both subtle and profound. Take a deep breath, settle in a little deeper, and let's continue our journey. In a universe where time has stopped, no wave of any kind could exist. And when you really think about this, it reveals just how fundamental waves are to everything around us. We often think of waves as something we see at the beach, water rising and falling in those mesmerizing rhythms. But waves are so much more than that. Light is a wave, an electromagnetic oscillation propagating through space. Sound is a wave, a compression wave traveling through air or water or solid matter. Heat transfers through radiation as waves. Radio signals, Wi-Fi, X-rays, microwaves, all waves. Even matter itself at the quantum level exhibits wave-like properties. Electrons exist as probability waves until observed. In fact, the very fabric of reality at its smallest scales is better described as fields of waves than as tiny particles. But waves, by their very nature, require oscillation. They require a back and forth, a rising and falling, a repeating pattern that propagates through space and time. And that word, time, is crucial. Without time, there can be no oscillation. The wave would freeze at whatever point in its cycle it happened to be when time stopped. An ocean wave might be captured at its crest, a permanent mountain of water. A sound wave might be frozen mid-compression, air molecules packed together in some places and spread apart in others, but never moving to create the next part of the pattern. Without waves, without this fundamental mechanism of propagation, the universe becomes a very different kind of place. Static, silent, dark, unchanging. And here's something that might not occur to you at first. The concept of speed becomes meaningless in a world without time. We measure speed as distance divided by time. Miles per hour, meters per second, kilometers per minute. Speed is fundamentally about how much distance is covered in a given duration. But if there is no duration, if time has stopped, then the entire concept falls apart. That car on the highway that was traveling at 70 miles per hour when time stopped, what is its speed now? It's not moving, so is it 0 miles per hour? But it's also not slowing down or speeding up. It's frozen at a moment when it had a specific velocity, a specific direction and magnitude of motion. Does that frozen state still count as speed? The answer is that speed as a concept only makes sense in a universe where time flows. You could say the car has a velocity vector, a direction and magnitude it would be moving if time were flowing, but calling it speed seems wrong because speed implies motion and motion implies time. Even the speed of light, that universal constant, that cosmic speed limit of approximately 186,000 miles per second, becomes a number without meaning. Light isn't moving anymore. Nothing is moving. Speed, velocity, acceleration, all these concepts we use to describe motion through space and time, they all require time to be meaningful. In a frozen universe, they're just abstract numbers attached to objects that aren't going anywhere. This leads us to an even stranger realization. Space would stop being navigable. Think about what it means to navigate, to move from one place to another. You want to go from here to there, so you travel the distance between. But traveling requires motion through time as well as space. You can't move through space without also moving through time. Even standing still, you're moving through time at 1 second per second, aging, experiencing the flow of moments. In physics, we talk about space-time as a unified four-dimensional structure, 3 dimensions of space and 1 of time, all woven together. You can't separate them. Every path through space is also a path through time. If time has stopped, you can't take any paths. You can't navigate anywhere because navigation requires a journey, and a journey requires duration. The distance between your current position and any other position still exists in some abstract sense. You could measure it with a ruler if rulers could move, but that distance can't be traversed. You're locked to your position in space just as firmly as you're locked to your moment in time. The universe becomes a map that can never be explored, a geography frozen into permanent inaccessibility. Every location exists, but none can be reached from any other. Space becomes a gallery of frozen positions, each thing forever in its place. Now, consider the observers in this frozen universe, or rather, the impossibility of observers. No observers could form memories, and without memories, consciousness itself becomes questionable. Memory is a process of encoding, storing, and retrieving information in the brain. When you experience something, neurons fire in specific patterns, proteins are synthesized, synaptic connections are strengthened or weakened. This is how a moment becomes a memory. But all of these processes require time. The electrochemical signals need time to propagate through neural networks. The proteins need time to be constructed by cellular machinery. The structural changes in synapses need time to occur and stabilize. Without time, none of this can happen. The last thing you experienced before time stopped would be frozen in your short-term memory, whatever was actively being processed by your brain at that instant. But it could never move into long-term storage. Could never be recalled later because there is no later. You couldn't form a memory of time stopping because forming that memory would require time to pass. And without the ability to form new memories, without the ability to create a continuous narrative of experience, can you really be said to be conscious? Consciousness seems to require a flow of mental states, one moment of awareness leading to the next, thoughts building on previous thoughts, sensations being processed and integrated. Take away the flow, freeze everything at a single instant, and consciousness becomes a snapshot, a frozen moment of awareness that can't develop, can't reflect, can't even know that it's frozen. This connects to something even more fundamental. No information could propagate in a frozen universe. Information theory tells us that information is, at its core, about differences and patterns and the transmission of those patterns from one place or time to another. When I speak to you, information travels from my brain to my vocal cords to the air to your ears to your brain. Each step requires time and motion. Sound waves must propagate. Neurons must fire. Signals must travel. But we've already established that waves can't exist and signals can't travel in frozen time. So information becomes trapped wherever it happens to be. The information encoded in a falling tree, the pattern of its trajectory and spin, is frozen with the tree. The information in a beam of light is frozen with the photons. The information in your brain's neural networks is frozen in whatever configuration it held at the moment time stopped. No computation can occur because computation requires information to move from one state to another, input to processing to output. No communication can happen because communication requires information to move from sender to receiver. The universe becomes filled with information that can't go anywhere or do anything. It's like having countless books that can never be opened, messages that can never be delivered, thoughts that can never be expressed. All the information is there, all the patterns and structures that encode meaning, but it's completely static, completely isolated, completely unable to interact or combine or create new patterns. And here's something that seems almost trivial but is actually quite profound. No clocks could ever restart themselves. Once time has stopped, there's no mechanism within the frozen universe that could cause it to start again. Clocks measure time, they don't create it. A pendulum swings because gravity pulls it and momentum carries it. But both of those processes require time. A digital clock counts oscillations in a quartz crystal, but oscillations require time. Even atomic clocks, the most precise timepieces we have, work by counting the oscillations of electromagnetic radiation absorbed or emitted by atoms transitioning between energy levels. But transitions require time, oscillations require time, counting requires time. If time has stopped, the clock can't tick. And more importantly, the clock can't somehow spontaneously start itself ticking again because that would require a change of state, and changes require time. It's a complete deadlock. The universe would be frozen in a self-sustaining state where nothing can change, and because nothing can change, there's no mechanism to unfreeze it. Time would have to be restarted from outside, by something or someone not subject to the freeze, which raises all sorts of philosophical and logical questions about what could possibly exist outside of time. In such a universe, the concept of now would lose meaning. We use the word now to refer to the present moment, the instant that divides past from future, the knife edge of time where things are actually happening. But now is only meaningful in contrast to then, to moments that have passed and moments yet to come. Now is a moving target, constantly shifting as time flows forward. The time when you started reading this was different from now, and by the time you finish the sentence, it will be different now again. But if time has stopped, there is no flow. There is no transition from one now to the next. There's just a single frozen state that could be called now, but it's a now that never becomes then, never gives way to a future now. It's an eternal present, But even calling it present seems wrong because present implies the existence of past and future, and in a frozen universe, those temporal categories might not apply. The past would still exist in some sense. It's the collection of all the states the universe went through before time stopped, frozen into the configuration of matter and energy at the moment of stopping. But the future would be blank, not just unknown but non-existent, not just unwritten but unwritable. And now would be everything and nothing, a moment stretched into eternity, a present with no presence. This leads to something deeply unsettling about predictability. The universe would lose its predictability, but not in the way you might think. When we say the universe is predictable, we mean that if you know the current state of a system and the laws of physics, you can calculate what will happen next. Newton's laws let you predict where a cannonball will land. Maxwell's equations let you predict how electromagnetic waves will behave. Quantum mechanics gives you probabilities for particle behavior. All of science is built on this idea that the present state determines, or at least constrains, future states. But in a frozen universe, there are no future states. The laws of physics become like a rulebook for a game that isn't being played. The equations still exist, the relationships they describe are still true in some abstract mathematical sense, but they have nothing to apply to because they're all equations about change over time. Newton's second law says force equals mass times acceleration, but acceleration is change in velocity over time. Maxwell's equations describe how electric and magnetic fields propagate, but propagation requires time. Even the conservation laws, which seem so fundamental, are about things being constant over time. If there's no time, what does conservation even mean? The universe would become utterly unpredictable, not because it's chaotic or random, but because the very concept of prediction requires a future to predict, and there is no future. But let's imagine, just for a moment, the impossible. Let's imagine that somehow, against all logic, time could restart. Perhaps some external force, some cosmic reset button, sets the flow of time moving again. And here's the terrifying part. Restarting time would be catastrophic, absolutely devastating in ways that are hard to even comprehend. Because while time was stopped, everything was frozen in mid-process. The bird was mid-wing beat. The water was mid-pour. The air molecules were scattered in patterns that only make sense as part of ongoing sound waves and air currents. Chemical reactions were half completed, with bonds broken but new ones not yet formed. And when time restarts, all of these interrupted processes would try to continue, but the universe they're continuing in is no longer consistent. Think about it. If time stopped for even a fraction of a second and then restarted, the momentum of every object would still be there, frozen, but every relationship between objects would be slightly off from where it should be. Worse, if time stopped for longer, things that should have changed didn't. The oxygen in your lungs should have been absorbed into your blood and replaced with carbon dioxide, but it wasn't. Your heart should have completed several beats, but it didn't. On a larger scale, the Earth should have rotated some amount, but it didn't. The planets should have progressed in their orbits, but they didn't. When time restarts, do all these things suddenly jump to where they should be? Does the Earth suddenly rotate to catch up? Do your cells suddenly age to account for lost time? Or does everything just continue from its frozen state, creating a universe that's fundamentally out of sync with its own laws? The restart might create shockwaves, discontinuities, a universe trying to reconcile its frozen state with the need to obey physical laws. It would be like taking a complex piece of machinery, stopping all its parts mid-motion, rearranging them slightly, and then expecting it to run smoothly. The universe itself might tear apart at the seams, unable to handle the contradiction between its frozen configuration and the flow of time being reimposed upon it. Now let your mind drift outward, beyond our frozen Earth, beyond the atmosphere, into the vast reaches of space. Let's explore what this time-stopped universe would mean for the cosmos itself, for the stars and galaxies and all the grand celestial machinery that fills the night sky. Close your eyes, breathe deeply, and let's journey to the heavens. In this frozen cosmos, stars would stop producing energy, and this is perhaps one of the most dramatic changes we could imagine. Stars are not static objects, though they appear unchanging in our night sky. They're actually roaring furnaces of nuclear fusion, where hydrogen atoms are crushed together under immense pressure and temperature to form helium, releasing tremendous amounts of energy in the process. Our sun, for instance, converts about 4 million tons of matter into pure energy every single second. Every second, that energy radiates outward as light and heat, the warmth that makes life on Earth possible, the light that brightens our days. But nuclear fusion is a process, a series of events that unfold over time. Hydrogen nuclei must collide with enough energy to overcome their electromagnetic repulsion. They must fuse, creating heavier elements. The energy released must propagate outward through the star's layers, eventually reaching the surface and radiating into space. If time stops, all of this stops. The collisions freeze mid-impact. The fusion reactions halt halfway through. The energy trapped in the star's core can't travel outward. A star frozen in time would be like a photograph of an explosion, all the violence and energy captured in a single instant but going nowhere, doing nothing. The star would still exist, all its mass still there, compressed and hot, but it would no longer be a living star. It would be a monument to a process that can no longer continue. Billions upon billions of stars across the universe, all going dark not by burning out but by simply stopping, frozen at whatever point they were in their life cycle when time ceased. And while we're thinking about processes that require time, consider this. Particle decay would halt mid-process, suspended at the quantum level. In our normal universe, many particles are unstable. They exist for a while and then decay into other particles, transforming according to the rules of quantum mechanics and the fundamental forces. A free neutron, for instance, will decay into a proton, an electron, and an antineutrino in about 15 minutes on average. Muons decay in microseconds. Some isotopes take billions of years to decay, while others exist for only tiny fractions of a second. This decay is happening all around us, constantly at every scale. It's part of how radioactive materials work, how carbon dating tells us the age of ancient objects, how particle physics experiments detect exotic particles. But decay is a process of transformation that unfolds over time. The particle exists in one state, quantum processes occur, and it transitions to another state. If time stops, particles that were in the middle of decaying would be frozen in some strange intermediate state. Quantum mechanics tells us that particles can exist in superpositions, in multiple states at once until measured or observed. A decaying particle might be caught between states, neither fully the original particle nor fully the decay products, just stuck in quantum limbo. Across the entire universe, countless trillions upon trillions of particles would be frozen at various stages of their decay processes, a cosmos of quantum states that can never resolve, never complete their transformations. In the vast spaces between stars, chemical reactions in space would halt mid-bond, frozen in the act of creation or destruction. You might think of space as empty, but it's not. It's filled with thin gases, dust, complex molecules drifting in the void. In giant molecular clouds, where new stars are born, chemistry happens. Atoms meet and bond, forming simple molecules like hydrogen gas, and sometimes more complex ones, water, ammonia, even organic compounds that are the building blocks of life. These reactions happen slowly compared to chemistry on Earth, where molecules are packed close together. In space, atoms and molecules are so spread out that they might drift for years before encountering another particle to react with. But when they do meet, when the conditions are right, bonds form. Electrons are shared between atoms. Energy states shift. New molecules are created. All of this requires time. The atoms must approach each other. The electrons must rearrange. The new bond must stabilize. With time frozen, you'd have molecules caught in the act of forming, atoms positioned next to each other, electron clouds beginning to overlap, but the bond not yet complete. Or you'd have molecules in the process of breaking apart, bonds weakening, atoms starting to separate, but not yet free. Throughout the universe, in every nebula and every dust cloud, chemistry would be suspended in countless moments of transition, potential reactions that can never finish. And speaking of particles in motion, neutrinos would be frozen passing through everything, and this creates a strange image. Neutrinos are among the most ghostly particles in physics. They have almost no mass, no electric charge, and they barely interact with other matter. Billions of neutrinos from the sun pass through your body every second, and you never notice because they almost never collide with anything. They stream through the Earth as if it weren't even there. They're produced in nuclear reactions, supernovas, cosmic ray collisions, all sorts of high-energy events throughout the universe. And they travel at nearly the speed of light, crossing vast distances of space. In a frozen universe, all those neutrinos would be stopped mid-flight. There would be neutrinos frozen inside the Earth, having entered one side and not yet exited the other. Neutrinos frozen inside the sun, created in fusion reactions and trying to escape. Neutrinos frozen in the space between galaxies, on journeys that might have taken millions of years. They wouldn't be visible, they're too small and too weakly interacting to see, but they'd be there, a vast invisible population of particles caught mid-journey, each one a messenger carrying information about some distant event, information that can now never be delivered. Similarly, cosmic radiation would be paused mid-impact, frozen at the moment of collision. Cosmic rays are high-energy particles, mostly protons, that travel through space at tremendous speeds, some of them moving at nearly the speed of light. When they hit Earth's atmosphere, they collide with atoms of nitrogen and oxygen, creating cascades of secondary particles, showers of muons and electrons and photons that rain down on the surface. These collisions are violent, energetic events. The cosmic ray particle approaches at relativistic speed. It strikes an atmospheric atom. The collision occurs, producing a spray of new particles, each carrying away some of the original energy. In a frozen universe, you'd have cosmic rays caught at every stage of this process. Some would be frozen in space, still approaching Earth. Some would be frozen at the moment of first impact, the cosmic ray touching the atmospheric atom but the collision not yet resolved. Some would be frozen mid-cascade, with secondary particles already created and flying outward but not yet hitting other atoms to create the next generation of the shower. It would be like a vast three-dimensional sculpture of particle physics, hundreds of thousands of cosmic ray events frozen in progress at any given moment, each one a snapshot of nature's particle accelerator in action. Now let's think about the universe's most mysterious objects. Black holes would stop growing, frozen at whatever size they'd reached when time stopped. Black holes grow by consuming matter. Gas and dust and sometimes entire stars fall into them, crossing the event horizon, that boundary beyond which nothing can escape. As matter falls in, the black hole's mass increases. Its event horizon expands. Its gravitational pull strengthens. But falling is a process that requires time. Matter spiraling into a black hole might take hours or days or years to finally cross the event horizon, depending on its initial trajectory. In a frozen universe, you'd have matter caught in the act of falling, some of it just beginning its death spiral, some of it on the final plunge toward the event horizon. But none of it could actually cross. None of it could add to the black hole's mass. The black hole would be frozen at its current size, surrounded by a frozen accretion disk of matter that's falling but can never fall, material that's being torn apart by tidal forces but can never complete its disintegration. Even stranger, the intense radiation emitted by material falling into black holes, those brilliant jets and X-rays that make some black holes the brightest objects in the universe, would be frozen mid-emission. The black hole would be surrounded by light that can't escape outward and matter that can't fall inward, everything locked in place around the frozen singularity. And this brings us to one of the more exotic consequences. Gravitational waves would be suspended in space, frozen ripples in the fabric of space-time itself. When massive objects accelerate, especially in violent events like two black holes merging or a supernova explosion, they create ripples in space-time that propagate outward at the speed of light. These are gravitational waves, stretching and squeezing space itself as they pass. We've only recently developed the technology to detect them, but they're happening all the time, countless events across the universe sending out these ripples. But waves require time to propagate. A gravitational wave is a changing distortion in space-time, a pattern that moves through space over time. With time frozen, gravitational waves would be caught mid-propagation. Imagine a ripple on a pond, frozen just as it spreads outward from where a stone hit the water. That's what gravitational waves would be like. Three-dimensional ripples in space-time itself, spreading out from their source but frozen, unable to travel further. The universe would be filled with these frozen distortions, each one a record of some catastrophic event, a black hole merger that happened 1 billion years ago or a supernova from last week, all equally frozen, all equally unable to continue their journey through space. Even more fundamentally, space-time curvature would be frozen mid-geometry, locked into whatever shape it had when time stopped. Einstein's general relativity tells us that mass and energy curve space-time, and objects follow the straightest possible paths through this curved geometry. That's what we experience as gravity. The Earth curves space-time around it, and we follow those curves, which keeps us on the surface. The Sun curves space-time more dramatically, and the planets follow those curves in their orbits. But here's the thing, space-time is dynamic. As objects move, the curvature changes. When the Earth orbits the Sun, it's constantly moving through the Sun's gravitational field, and the exact shape of space-time is constantly shifting to account for the Earth's changing position. With time frozen, space-time curvature would be locked in place. The Earth would be frozen at one point in its orbit, and the space-time around it would be curved in exactly the way it was at that instant, but it couldn't evolve, couldn't change as motion continues. The dynamic dance between matter and space-time geometry would become a static sculpture. Every planet is frozen in its orbital position. Every galaxy is frozen in its rotation. All the curvature locked in place, a geometry that describes motion but cannot support it. This frozen geometry would have profound implications for the cosmos as a whole. Cosmic structure formation would halt permanently, ending the universe's long journey toward complexity. In the early universe, matter was spread almost uniformly, just a thin soup of particles. But tiny density fluctuations, quantum fluctuations stretched to cosmic scales during inflation, meant some regions were slightly denser than others. And those denser regions had slightly stronger gravity, attracting more matter, becoming denser still. Over billions of years, this process created structure. Gas clouds collapsed to form the first stars. Stars clustered into galaxies. Galaxies clustered into groups and clusters and superclusters, creating the cosmic web we observe today, vast filaments of matter surrounding enormous voids. This process is still ongoing. Galaxies are still moving, still clustering. Small galaxies are merging into larger ones. Gas is still collapsing into new stars. But all of this requires time. Gravity must pull. Matter must move. Collisions must occur. In a frozen universe, structure formation would stop wherever it was. Galaxies caught mid-merger would never complete their collision. Gas clouds starting to collapse would never form stars. The universe's evolution toward ever more complex structure would simply end, leaving the cosmos in whatever state of partial completion it had reached, a universe frozen partway through its own development. And finally, on the grandest scale imaginable, biological time at the cosmic scale would vanish, and with it, any possibility of life's story continuing. Life, wherever it exists in the universe, is a process. Growth, reproduction, evolution, metabolism, all the things that define living systems require time to unfold. A seed must grow into a tree over years. A species must evolve over generations. Even a single heartbeat requires time. In our discussion earlier, we talked about how individual organisms would be frozen, unable to breathe or think. But zoom out and consider life on a cosmic scale. On Earth, life has been evolving for billions of years. Simple cells giving rise to complex organisms, generation after generation, mutation and selection and adaptation creating the incredible diversity we see today. And Earth might not be alone. There might be life on distant planets, perhaps in the oceans of Europa or Enceladus, perhaps on worlds around other stars. Each of these biospheres, if they exist, would have their own story, their own evolutionary trajectory. But with time frozen, all of that stops. The tree of life on every world would be frozen at whatever branch it had reached. Species mid-evolution would never complete their transformations. Organisms in the process of being born would never fully emerge. The grand story of life in the universe, that ongoing narrative of biological complexity emerging from chemistry and physics, would end mid-sentence. Not because life died, but because the very concept of biological time, of life's processes unfolding, would cease to have meaning. Now, as you relax even more deeply, let's contemplate the most fundamental aspects of our universe itself. What would happen to the very fabric of existence, to the universe as a whole, if time were to stop? Breathe slowly, let your thoughts drift, and journey with me to the ultimate consequences of frozen time. Perhaps the most staggering realization is that the expansion of the universe would freeze, halting the most fundamental motion in all of existence. Since the Big Bang, the universe has been expanding. Every galaxy is moving away from every other galaxy, not because they're traveling through space, but because space itself is expanding, stretching like the surface of an inflating balloon. We've measured this expansion. We've watched distant galaxies receding from us, their light shifted toward the red end of the spectrum by the stretching of space. The farther away a galaxy is, the faster it appears to recede. This expansion is written into the very equations of general relativity. It's not just things moving through the universe, it's the universe itself growing, space itself stretching. But expansion is a process that occurs over time. The distance between galaxies increases as time passes. Space expands from one moment to the next. If time stops, this expansion must stop too. The universe would be frozen at whatever size it had reached, whatever scale factor it had achieved at the moment of stopping. Galaxies would be locked at their current distances from each other, never growing farther apart, but also never coming closer. The cosmic horizon, that limit beyond which light hasn't had time to reach us since the Big Bang, would be frozen in place. The universe would still be vast, still be filled with billions of galaxies, but it would no longer be a growing, evolving cosmos. It would be a fixed structure, eternal and unchanging in its spatial extent. And within this frozen cosmos, light already in transit would be stuck forever, frozen photons carrying messages that can never be delivered. Right now, at this very moment, space is filled with light. Photons from distant stars, traveling for millions or billions of years, still making their way toward us. Light from our own sun, taking 8 minutes to reach Earth, spread across 93 million miles of space. Light from galaxies so distant that it's been traveling since before Earth formed, perhaps even since the universe was young. All of this light is in motion, photons streaming through the void at the cosmic speed limit. But if time stops, those photons stop too. They wouldn't disappear. They'd still exist, still carry their energy and frequency and polarization, but they'd be frozen in position, scattered throughout the universe like an invisible mist. A photon that was halfway between a distant quasar and Earth would remain halfway, never completing its journey. Light that was just about to enter a telescope, about to strike a detector and be recorded by human instruments, would hang there 1 nanometer away, eternally close but never arriving. The universe would be filled with frozen light, photons locked in space, each one carrying information about its source, information about temperature and composition and motion, but all of it inaccessible, all of it trapped in transit, messages written but never read. Among this frozen light would be something particularly special. The Big Bang's echo would be locked in place, the cosmic microwave background radiation frozen at whatever point in its journey it had reached. This radiation is the oldest light in the universe, released about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light to travel freely. It's been streaming through space ever since, gradually cooling as the universe expands, stretched from visible light to microwaves by the expansion of space itself. Today, it fills the entire universe, a nearly uniform glow coming from every direction, at a temperature just under 3 degrees above absolute zero. This is our baby picture of the universe, the afterglow of creation, and by studying its tiny fluctuations, we've learned about the early universe's structure, composition, and evolution. But in a frozen universe, this ancient light would be stuck wherever it was. The photons that make up the cosmic microwave background would be frozen in their current positions, at their current wavelengths. The information they carry about the early universe would still be encoded in them, in their temperature variations and polarization patterns, but it would be frozen information, unable to propagate, unable to reach new observers or new instruments. The echo of the Big Bang would still exist, but it would be a silent echo, locked in place, unable to travel. Even more fundamentally, cosmic inflation would lock into a single value, frozen at whatever state the inflaton field happened to be in. Inflation is a theory about the very earliest moments of the universe, a period of exponential expansion that occurred in the first tiny fraction of a second after the Big Bang. During inflation, space expanded incredibly rapidly, driven by a quantum field called the inflaton field. When inflation ended, the energy in this field decayed into particles and radiation, creating the hot, dense state we associate with the traditional Big Bang. But fields, even quantum fields, evolve over time. The inflaton field had to roll down its energy landscape, like a ball rolling down a hill, until it reached a minimum and inflation ended. If time stopped, the inflaton field, if it still exists anywhere in our universe or beyond, would be frozen at whatever value it had. If inflation was still occurring somewhere, it would stop, the field locked at a particular energy level, the exponential expansion halted. If inflation had already ended everywhere, the remnants of the inflaton field would be frozen in their post-inflation state. The quantum fluctuations in the inflaton field, which became the seeds of cosmic structure, would be frozen as they were, unable to evolve further. This is subtle and strange to think about because inflation happened so long ago, but in some models of cosmology, inflation might still be occurring in distant regions beyond our observable universe, creating new bubble universes. In a time-stop scenario, all of that would freeze, the multiverse itself, if it exists, locked into a single configuration. This brings us to perhaps the most profound change of all. Entropy would stop increasing, violating what might be the universe's most fundamental law. The second law of thermodynamics states that the total entropy of an isolated system always increases over time. Entropy is a measure of disorder, of the number of possible microscopic arrangements consistent with a system's macroscopic state. Things tend to evolve from ordered states to disordered ones because there are vastly more disordered arrangements than ordered ones. A broken egg is more likely than an intact one because there are countless ways for an egg to be broken but only one way for it to be whole. This is why time seems to have a direction, why we remember the past but not the future, why causes precede effects. Entropy gives time an arrow, but entropy increase requires change over time. Ordered systems must evolve into disordered ones. Heat must flow from hot to cold. Structures must decay. In a frozen universe, none of this can happen. The entropy of the universe would be locked at whatever value it had when time stopped. Ordered systems would stay ordered. Disordered systems would stay disordered. Heat wouldn't flow because flow requires time. Structures wouldn't decay because decay requires time. The universe would be frozen at a particular point on its long journey toward maximum entropy, toward the heat death that awaits in the distant future. It would be like stopping a movie mid-frame, the story incomplete, the ending never reached. And without entropy increasing, without time flowing forward, no notion of irreversibility could exist. Irreversibility is the idea that some processes can't be undone, that you can't unscramble an egg or unburn a piece of wood or unmix cream from coffee. These processes are irreversible because they involve increases in entropy, movement from unlikely ordered states to likely disordered ones. The mathematics of physics at the microscopic level are actually reversible. If you filmed molecules bouncing around and played the film backward, it would look just as plausible. But at the macroscopic level, we never see entropy spontaneously decreasing, never see the disordered molecules arranging themselves back into ordered configurations. This is irreversible, and it's deeply connected to the flow of time. In a frozen universe, the concept becomes meaningless. Nothing can be reversed because nothing can change at all. But also, nothing can be completed in the first place, so there's nothing to reverse. Broken eggs aren't becoming more broken. Burned wood isn't turning to ash. Everything is frozen mid-process, neither reversible nor irreversible, just static. The arrow of time, that fundamental asymmetry that makes the past different from future, would disappear because there would be no past and future, only the eternal frozen now. This creates a strange problem for the universe's age. The universe's age becomes undefined, not in the sense that we don't know it, but in the sense that age as a concept loses meaning. Right now, we can say the universe is approximately 13.8 billion years old. We measure this by looking at the expansion rate, the cosmic microwave background, the ages of the oldest stars. All of these are measurements of how much time has passed since the Big Bang. But time past is a concept that requires time to flow. In a frozen universe, no more time can pass, so no more aging can occur. The universe wouldn't get older. But can we even say it has an age? Age is usually defined as the duration from some starting point to now. But if there's no flow of time, is there really a now in the sense we normally mean? The universe would exist in a state that was 13.8 billion years after the Big Bang. But calling this an age seems wrong because age implies ongoing duration, implies that time continues to accumulate. It would be more accurate to say the universe exists at a temporal coordinate, a point on the timeline of a universe that no longer has a functioning timeline. The age would be a frozen number, neither increasing nor decreasing, a label for the temporal position where everything stopped but not a measure of ongoing duration. What we're describing really is that the universe becomes a perfect snapshot, not a process. We often think of the universe as a story, a narrative unfolding from the Big Bang to the present and onward to the future. Events happen. States transition to other states. Causes produce effects. The universe evolves, develops, grows in complexity. But a snapshot is different. A snapshot is a single frozen image, all the information about one moment captured and preserved. In a time-stopped universe, everything would be like that. All the matter and energy, all the fields and particles, all the structures from atoms to galaxies, they'd still exist, but they'd exist as a static configuration, like a three-dimensional sculpture of unimaginable complexity, or a computer simulation paused mid-calculation. Every detail would be preserved, every position of every particle, every value of every field. But there would be no dynamics, no evolution, no story. Scientists could, in principle, examine this frozen state and learn about the universe's properties, its composition, its structure at the moment of freezing. But they couldn't watch processes unfold. They couldn't run experiments over time. They couldn't observe cause and effect. The universe would be pure data, pure information about a single moment, with no before or after to give that moment context or meaning. And in this frozen state, the universe becomes a single eternal state, unchanging and permanent in a way that almost seems peaceful. In our flowing universe, nothing lasts. Stars are born and die. Galaxies merge and disperse. Even atoms eventually decay. Everything is temporary, existing for a while and then transforming into something else. This impermanence can seem sad, but it's also what makes the universe dynamic and interesting. Change is what creates novelty, what allows new structures to form, new possibilities to be explored. But in a frozen universe, there would be no impermanence because there would be no change. Whatever exists would exist forever, exactly as it is. That bird frozen mid-flight would never land, but it would also never fall. It would be eternally in flight, or rather, eternally in the appearance of flight. The wave frozen at its crest would never crash on the shore, but it would also never collapse. It would be an eternal crest, a permanent peak. There's something almost serene about this, if you can look past the horror of it. No more loss because nothing can be lost. No more endings because nothing can end. Just eternal, unchanging existence. Of course, there would also be no new beginnings, no growth, no creation. But what exists would be, in a sense, immortal, preserved forever in its frozen state, like insects trapped in amber, but on the scale of the entire universe. And this leads us to the final, most abstract realization. Reality would reduce to pure structure, to pattern without process, to form without function. Structure is about how things are arranged, how they relate to each other spatially and organizationally. A crystal has structure, atoms arranged in a repeating lattice. A galaxy has structure, stars organized in spiral arms or elliptical distributions. DNA has structure, base pairs arranged in a specific sequence along a double helix. All of this structure would still exist in a frozen universe. The arrangements, the relationships, the patterns would all be preserved. But structure usually serves a purpose, enabling some process or function. The structure of DNA enables replication and protein synthesis. The structure of a galaxy reflects its rotational dynamics. The structure of a crystal determines its physical properties. But all of these functions require time to manifest. DNA can't replicate without time. Galaxies can't rotate without time. Crystals can't interact with light or conduct heat without time. So in a frozen universe, structure would remain but function would vanish. The universe would become a purely geometric entity, a mathematical object, a pattern frozen in three-dimensional space. All the beauty of that pattern would still be there, all the intricate complexity built up over billions of years of cosmic evolution. But it would be dead beauty, frozen beauty, structure without purpose, pattern without meaning. A universe reduced to its most abstract form, pure information encoded in the arrangement of frozen matter and energy, with no dynamics to bring that information to life. And now, as you drift deeper into relaxation, let's explore something even more fundamental. Let's examine what happens to the very laws of physics themselves when time stops. The mathematical framework that describes reality, the elegant equations that govern everything from falling apples to expanding universes. Breathe slowly, let your mind float freely, and contemplate with me the breakdown of physics itself. At the most fundamental level, causality itself would be suspended, And this is perhaps the deepest violation imaginable. Causality is the principle that causes precede effects, that one event can influence another event that happens later. You flip a switch and then the light comes on. A star explodes in a supernova, and then, years later, the light from that explosion reaches Earth. The present state of the universe is caused by, or at least constrained by, previous states. This seems so obvious, so built into our understanding of reality, that it's hard to imagine things any other way. But causality is inherently temporal. It requires a sequence of events, a before and after, a this then that. Without time, there can be no sequence. There can be no before and after. Events don't follow from other events because there's no following, no progression, no unfolding. In a frozen universe, you'd have configurations of matter and energy that look like they should have causal relationships. You'd see a ball positioned as if it had been thrown, suspended in midair. You could trace backward and identify what must have caused it to be there. But the actual causal chain, the actual sequence of events where the thrower's hand pushed the ball and set it in motion, that sequence can't exist without time. Causality would be frozen along with everything else, reduced to a pattern that suggests cause and effect but contains no actual causation, no actual flow from one state to another. And without causality, without time, no equations of motion would exist in any meaningful sense. Physics is built on equations of motion, mathematical descriptions of how systems change over time. Newton's laws tell you how forces cause acceleration, how position changes with time. The Schrödinger equation tells you how quantum states evolve. Maxwell's equations tell you how electromagnetic fields propagate. Einstein's field equations tell you how spacetime curvature evolves in response to matter and energy. Every fundamental equation in physics is, at its heart, an equation about change over time. They're differential equations, expressing how some quantity varies from one instant to the next. But in a universe without time, without instants following one another, these equations become meaningless. They don't become false exactly. The relationships they describe might still hold in some abstract sense. But they have nothing to apply to. There's no evolution to calculate, no change to predict. The equations would be like instruction manuals for machines that don't exist, or recipes for meals that can never be cooked. All the mathematical machinery we've developed to describe the physical world, centuries of brilliant insights encoded in elegant equations, would become empty formalism, true but irrelevant, describing a kind of change that cannot occur. This extends to something more abstract. No mathematical evolution operators would work, and this might sound technical, but it gets at something deep. In physics and mathematics, we often describe change using operators, mathematical objects that transform one state into another. The time evolution operator in quantum mechanics, for instance, takes the state of a system at one time and tells you what state it will be in at a later time. The exponential of the Hamiltonian evolving states along the flow of time. Similarly, in classical mechanics, you have operators that propagate solutions forward in time. In field theory, in statistical mechanics, in every branch of physics, there are mathematical structures specifically designed to capture how things evolve temporally. But evolution requires time. These operators are fundamentally about mapping between different moments, about connecting past to future. In a frozen universe, there's only one moment, one state, no past or future to connect. The evolution operators would have no domain to operate on, no transformation to perform. They'd be like functions with no input, maps of a journey that never takes place. The mathematical framework we use to describe change would become a scaffold for a building that was never constructed. Even more fundamentally, no reference frame could exist in the way we normally understand them. A reference frame in physics is a coordinate system, a way of assigning positions and times to events. You might use a reference frame attached to Earth, or one attached to a moving train, or one floating in space. Different frames assign different coordinates to the same event, but they're related by precise mathematical transformations. Crucially, a reference frame includes not just spatial coordinates but a time coordinate as well. Events are labeled by when and where they occur, but in a frozen universe, the time coordinate becomes problematic. If time isn't flowing, if there's no succession of moments, what does the time coordinate even mean? You might still label the frozen state with some time value, the moment when time stopped, but it wouldn't be a coordinate in the usual sense because coordinates are supposed to allow you to locate things within a space, and a single moment isn't a space you can navigate. The reference frame would collapse from 4 dimensions to 3, losing its temporal component. And worse, reference frames are usually understood as viewpoints from which observers can make measurements over time. But there are no observers in frozen time, no measurements occurring, no viewpoint that can shift or change. The concept of a reference frame would become a mathematical ghost, a structure that seems like it should exist but has lost the physical grounding that gave it meaning. This creates another impossibility. No frame could observe relativistic effects, those strange phenomena that emerge when things move at speeds close to the speed of light. Time dilation, where moving clocks tick slower. Length contraction, where moving objects appear shorter along their direction of motion. The relativity of simultaneity, where events that are simultaneous in one frame occur at different times in another. All of these effects depend on relative motion between reference frames, and crucially, they depend on time. Time dilation is meaningless without time passing. It's the rate at which time flows that changes, but if time isn't flowing at all, there's no rate to change. Length contraction depends on comparing the length of an object in its rest frame to its length in a frame where it's moving, but motion requires time. Simultaneity is about whether events happen at the same time or different times in various frames. But without time flowing, the concept of happening doesn't apply. A universe frozen in time would be a universe where special relativity's most distinctive predictions become undefined. Not violated because you can't violate a law that doesn't apply, but simply outside the domain where the theory has meaning. Relativistic effects would be frozen potential mathematical relationships that could describe things if time were flowing but that have no manifestation in a static universe. In this frozen world, electromagnetic fields would lock in place, frozen patterns of electric and magnetic force extending through space. Right now, electromagnetic fields are dynamic. They oscillate, creating light waves. They propagate, carrying energy from one place to another. A changing electric field creates a magnetic field. A changing magnetic field creates an electric field. This interplay, this mutual creation, is what allows electromagnetic waves to exist and travel. But change requires time. In frozen time, electric fields would be frozen in whatever configuration they had. Magnetic fields would be frozen too. The fields would still exist, they'd still have magnitude and direction at every point in space, but they couldn't change, couldn't oscillate, couldn't propagate. Light, as we discussed earlier, would be frozen. But it's worth emphasizing that this means the electromagnetic field itself is frozen. Not just the photons, but the underlying field that photons are excitations of. The field would be a static landscape, hills and valleys of electric and magnetic potential, but completely unchanging. No waves rippling across it. No disturbances traveling through it. Just a frozen geometry of force, potential energy locked in configuration, unable to do work, unable to affect charges, unable to propagate or evolve. This frozen state would also mean that no symmetry transformations could be applied, at least not in the usual dynamical sense. Symmetry is a profound concept in physics. When we say a system has a symmetry, we mean there's a transformation you can apply that leaves the system unchanged or changes it in a predictable way. Rotational symmetry means you can rotate something and it looks the same. Translational symmetry means you can shift it in space and it's unchanged. Time translation symmetry means the laws of physics are the same at different times. These symmetries are connected to conservation laws. Time translation symmetry gives you conservation of energy. Space translation symmetry gives you conservation of momentum. In a frozen universe, some symmetries might still exist in a static sense. Rotational symmetry of a sphere, for instance, is a geometric property that doesn't require time. But dynamical symmetries, transformations that involve evolution or change, would be undefined. You can't apply a time translation because there's no time to translate through. You can't evolve a system forward and check if the laws remain the same because there's no forward to evolve toward. And some symmetries are fundamentally about transformations over time, like Lorentz boosts that change your reference frame to one moving at a different velocity. Without time, without the possibility of motion, these transformations lose their meaning. Among the most fundamental symmetries is CPT symmetry, and this would be undefined in frozen time. CPT symmetry is a theorem in quantum field theory stating that the combined operation of charge conjugation, parity inversion, and time reversal is a symmetry of all physical processes. Charge conjugation swaps particles with antiparticles. Parity inversion reflects space through a mirror. Time reversal, as the name suggests, reverses the direction of time. CPT symmetry says that if you take any physical process, swap all particles with antiparticles, mirror reflect it, and run it backward in time, you get another valid physical process. This symmetry is deeply connected to the structure of quantum field theory and the properties of spacetime. But notice that crucial component, time reversal, the T in CPT. In a universe where time has stopped, where there's no flow of time to reverse, what does time reversal even mean? You can't reverse what isn't flowing. The symmetry operation becomes undefined, not because it's violated, but because one of its component operations, time reversal, has no referent in a timeless universe. CPT symmetry would be a theorem about a concept, time, that no longer exists. The mathematical structure would remain pristine and elegant, but without the physical substrate it was designed to describe. At an even deeper level, the universe's dimensional structure would break in a fundamental way. We describe spacetime as four-dimensional, 3 dimensions of space and 1 of time. These aren't separate things arbitrarily combined. They're woven together into a unified structure where spatial and temporal measurements mix depending on your state of motion. Moving through space affects how you experience time. Moving through time, which we all do constantly, is as fundamental as existing in 3 spatial dimensions. But if time stops, does space-time collapse to just space? Does the universe become 3-dimensional instead of 4-dimensional? This isn't just about losing a coordinate. It's about the structure of reality itself changing. In general relativity, space-time is a manifold, a smooth geometric structure where every point represents an event, a specific location in space at a specific moment in time. The curvature of this 4-dimensional manifold is what we experience as gravity. But a manifold needs all its dimensions to be a proper manifold. If you try to remove the time dimension, if you try to freeze everything at one moment, you're left with a 3-dimensional spatial slice, but it's not clear this slice is a complete spacetime anymore. It's more like a cross-section, a snapshot, lacking the full dimensionality that gives spacetime its structure. The universe would be dimensionally deficient, missing a crucial component of its geometric nature. And finally, in this broken physics, topological changes in spacetime would freeze, and topology is about the global structure, the shape and connectedness of space. In our universe, spacetime can undergo topological changes. In some theories of quantum gravity, spacetime might branch or merge, wormholes might form and collapse, the very topology might be dynamic and fluctuating, especially at tiny scales near the Planck length. Even in classical general relativity, you can have situations where the topology of space changes over time. A simple example might be two separate regions of space connected by a forming wormhole, changing the topology from two disconnected pieces to one connected piece. But these changes, like all changes, require time to occur. They're processes with a before and after, an initial topology and a final topology. In frozen time, any topological change in progress would halt mid-transformation. If a wormhole was in the process of forming, it would be frozen in some intermediate state, neither fully formed nor fully absent, just a partial connection, a half-complete tunnel through space-time. The topology would be locked at whatever configuration it had reached, unable to complete its transformation. And at the quantum level, if space-time really does fluctuate and foam and change topology wildly at tiny scales, all of that would freeze too. The quantum foam would become quantum ice, frozen in one configuration out of the countless possible configurations it would normally fluctuate through. Space-time would lose its dynamism, its ability to shift and change shape, becoming a rigid, unchanging topology, locked into a single geometric and topological form for eternity. As you continue to relax, breathing gently and easily, let's explore another layer of this impossible scenario. What happens to the very act of knowing, of measuring, of defining the properties of things? Let your mind drift through these quiet contemplations as we examine how measurement and matter itself lose meaning when time stops flowing. In a frozen universe, no measurement could be made, and this cuts to the heart of what it means to know anything about the physical world. Measurement is an interaction between a measuring device and the thing being measured. You want to know the temperature, so a thermometer interacts with the object, thermal energy flows until they reach equilibrium, and the thermometer's reading changes to indicate the temperature. You want to know the position of an electron, so you bounce a photon off it and detect where the photon goes. You want to know the mass of something, so you weigh it, observing how gravity pulls it down or how much force is needed to accelerate it. Every measurement is a process that unfolds over time. Energy must flow. Signals must propagate. Detectors must respond. In frozen time, none of this can happen. The thermometer can't equilibrate because equilibration is a process requiring time. The photon can't bounce and travel to a detector because that requires time. The scale can't respond to weight because response requires time. More fundamentally, the measuring device itself is frozen. Its internal mechanisms, whether they're mechanical gears or electronic circuits or quantum states, can't change to register the measurement. A measurement is fundamentally about one system affecting another system in a way that leaves a record, an imprint, a change in the measuring device that corresponds to a property of the measured system. But change requires time. Without time, there can be no measurements, no readings, no records. The universe would be full of things with properties, electrons with positions, objects with temperatures, but no way to determine what those properties are. And this leads to something even more troubling. No physical quantity could be operationally defined when time cannot flow. In physics, we define quantities operationally, in terms of the measurements or procedures used to determine them. Length is defined by laying down measuring rods or timing how long light takes to travel a distance. Time itself is defined by counting oscillations of cesium atoms or other periodic processes. Charge is defined by how much force it experiences in an electric field. Every quantity we talk about in physics is ultimately grounded in some operation, some procedure you could in principle carry out to measure it. But procedures require time. You have to do something, then observe the result. You have to set up an experiment, let it run, and record the outcome. In frozen time, you can't carry out procedures. You can't set up experiments or let them run or record outcomes. So how would you define anything? You might say that length is still length, it's the spatial extent of an object, and that doesn't depend on measuring it. And in a sense, that's true. Objects still occupy space, still have spatial extent. But without the ability to measure, without operational definitions grounded in actual procedures, these quantities become abstract, detached from any empirical content. They are mathematical properties of a mathematical model, but they've lost their connection to physical reality, to things you could in principle determine or verify. Physics would become purely theoretical, completely severed from experiment and observation. In this strange state, constants would exist but be untestable, frozen into the fabric of reality but completely inaccessible to verification. The universe has fundamental constants: the speed of light, Planck's constant, the gravitational constant, the charge of an electron, and many others. These constants appear in all our physical equations, determining the strength of forces, the scale of quantum effects, the relationship between energy and mass. We've measured these constants to incredible precision through countless experiments. But experiments require time. Measuring the speed of light requires sending light across a known distance and timing how long it takes. Measuring Planck's constant requires quantum phenomena that evolve over time. Measuring the gravitational constant requires observing how masses attract over time. In a frozen universe, you couldn't perform any of these measurements. The constants would still be there in some sense. They'd still be the numbers that characterize the frozen configuration of fields and particles, but you couldn't test them, couldn't verify them, couldn't even measure them for the first time if you somehow didn't already know them. They'd be like the hidden structure of a locked box, properties that determine everything about how the box is made, but that can never be examined or confirmed. The constants would exist as mathematical parameters of a frozen reality, untouchable and unknowable. Consider something as fundamental as mass. Mass would lose operational meaning in a universe where time has stopped. We think of mass as the amount of matter in an object, but operationally, we define it in terms of how it behaves. Gravitational mass is how much an object responds to gravity, how much force gravity exerts on it. Inertial mass is how much an object resists acceleration, how much force you need to apply to change its velocity. These two definitions turn out to give the same value, which is one of the deep insights that led Einstein to general relativity. But notice that both definitions involve processes over time. Gravitational mass is measured by letting gravity pull on something and seeing how it falls, which requires time. Inertial mass is measured by applying force and observing acceleration, change in velocity over time. In frozen time, you can't measure either kind of mass. Objects still have mass in the sense that they still have a certain amount of energy localized in their rest frame, and mass-energy equivalence tells us that this energy corresponds to mass. But you can't determine what that mass is. You can't weigh things. You can't push them and see how they accelerate. Mass becomes a frozen property, encoded in the frozen structure of matter and fields, but not accessible through any operational procedure. It exists but cannot be known. At a deeper mathematical level, phase space collapses to a single point, and this is a profound loss of structure. In physics, phase space is an abstract space where each point represents a possible state of a system. For a simple particle, phase space has 6 dimensions: 3 for position and 3 for momentum. Every possible combination of where the particle could be and how fast it could be moving corresponds to a point in this 6-dimensional space. As the system evolves over time, it traces out a path through phase space, moving from one state to another. For complex systems with many particles, phase space is vastly higher dimensional, but the idea is the same. The system's evolution is a trajectory through this space of possibilities. But in frozen time, there's no evolution, no trajectory. The system is at one point in phase space, the point corresponding to its frozen state, and it never moves to any other point. The entire infinite dimensional space of possibilities collapses to a single point, the one state that actually exists. All the other points, all the other possible states the system might have been in or might evolve into, they're still there mathematically, but they're not accessible, not reachable. The rich structure of phase space, with its volumes and flows and conserved quantities, reduces to a single frozen dot. Similarly, no probability distributions could update in a world where time has stopped. Probability in physics is often about our uncertainty, about the many possible outcomes of a situation when we don't have complete information. You might not know exactly where an atom is, so you describe it with a probability distribution, a cloud of possibilities centered on its most likely position. As you make measurements, as you gain information, you update your probabilities. The distribution narrows, concentrating on the outcomes consistent with your new knowledge. This updating happens over time. You make a measurement which takes time, and then you revise your probabilities based on what you learned. In frozen time, you can't make measurements, so you can't gain information, so you can't update your probabilities. But more fundamentally, probability distributions in quantum mechanics aren't just about our knowledge. They're about the physical state of the system. An electron really is in a superposition of positions until measured, described by a wave function that gives the probability amplitude for finding it at each location. And this wave function evolves over time according to the Schrödinger equation. It spreads out, interferes with itself, collapses upon measurement. All of this requires time. In frozen time, probability distributions would be frozen. An electron's wave function would be locked in whatever configuration it had, neither spreading nor concentrating, neither interfering nor collapsing. Probability would become static, a frozen map of possibilities that can never be explored or updated. This frozen quantum state means that quantum uncertainty would collapse into a snapshot, preserved but not evolving. Heisenberg's uncertainty principle tells us there are fundamental limits to how precisely we can know certain pairs of properties simultaneously. Position and momentum, for instance. The more precisely you know where a particle is, the less precisely you can know how fast it's moving, and vice versa. This isn't about measurement limitations or lack of information. It's a fundamental feature of quantum reality. Particles don't have definite positions and momenta simultaneously. They're described by wave functions that encode probabilities for both. And these wave functions evolve, spreading out in position space while concentrating in momentum space, or the reverse, always respecting the uncertainty principle. In frozen time, this dynamic uncertainty would become static. A particle's wave function would be frozen in whatever spread it had. If it was very localized in position, uncertain in momentum, it would stay that way. If it was spread out over a large region, it would remain spread out. The uncertainty would still be there, the particle would still not have a definite position and momentum, but the quantum state wouldn't evolve, wouldn't change its degree of uncertainty or trade uncertainty in one variable for uncertainty in another. It would be quantum mechanics without the mechanics, uncertainty without the evolution that normally gives quantum uncertainty its dynamic character. And in this static quantum realm, no probability amplitudes could interfere, cutting away one of quantum mechanics' most distinctive features. Interference is what makes quantum mechanics strange and beautiful. A particle can go through two slits simultaneously, following both paths, and the probability amplitudes for the two paths can interfere, adding constructively in some places and destructively in others, creating an interference pattern. This isn't just a mathematical trick. It's been verified in countless experiments with photons, electrons, even large molecules. The interference pattern builds up over time as particles arrive at a detector one by one. But interference requires the probability amplitudes to propagate, to evolve from their initial state through the slits to the detector. It requires the quantum state to develop over time. In frozen time, a particle's probability amplitude would be frozen wherever it was in its evolution. If it was mid-flight, traveling from the slits toward the screen, it would be frozen in that state of being spread across both paths. But it couldn't continue propagating, couldn't reach the screen, couldn't interfere with itself to create the pattern. The potential for interference would be there, encoded in the frozen wave function, but the actual interference, the dynamic process where amplitudes combine and create observable patterns, that couldn't happen. Quantum interference requires time, requires the wave function to evolve and overlap with itself, and without time, it remains a frozen possibility, never actualized. Even stranger, at the quantum vacuum level, virtual particles would freeze their fluctuations, locking the vacuum into one configuration. Quantum field theory tells us that empty space isn't really empty. The vacuum is full of quantum fields, and these fields fluctuate, creating pairs of virtual particles that pop into existence and annihilate each other in tiny fractions of a second. These fluctuations aren't just theoretical. They have measurable effects like the Casimir force and the Lamb shift, subtle influences on real particles and fields that we can detect experimentally. But fluctuations require time. A virtual particle pair must come into existence, exist for a brief moment, and then annihilate. That's a sequence of events, a process unfolding over time, even if it's an incredibly short time. In frozen time, the quantum vacuum would be locked in one particular configuration of its fluctuations. Virtual particles that had just been created would be frozen in existence, unable to annihilate. Virtual particles that were about to be created never would be. The vacuum would stop fluctuating, stop seething with quantum activity, and become a static configuration of fields and virtual particles. The zero-point energy would still be there, the minimum energy that quantum fields must have even in their ground state, but it would be frozen energy, unable to fluctuate or create new particle pairs or affect real particles in dynamic ways. And finally, vacuum energy itself would become observationally irrelevant in this frozen cosmos. Vacuum energy, or dark energy as it's sometimes called, is the mysterious energy density of empty space that's driving the accelerated expansion of the universe. It's incredibly small but not zero, and it has profound effects on cosmic evolution. Over billions of years, it causes the expansion of the universe to accelerate, pushing galaxies apart faster and faster. But this effect requires time to manifest. The vacuum energy is constant, the same at every point in space and every moment in time, but its influence on the universe's expansion accumulates over time. The universe has to expand for the effects of vacuum energy to be observable. In frozen time, with the expansion itself frozen, vacuum energy would just be a number, a constant energy density filling all of space. It would still be there, still contributing to the stress-energy tensor, still curving space-time in the way that general relativity describes. But you couldn't observe its effects because those effects are about change over time, about how the expansion rate evolves, about the ultimate fate of the universe billions of years from now. Vacuum energy would be a frozen property of a frozen space-time, as inaccessible and irrelevant as all the other quantities that require time to manifest or measure. As you settle even deeper into relaxation, you're breathing slow and steady. Let's explore yet another dimension of this frozen reality. Let's think about information, computation, and the very structure of complexity itself. Let your thoughts drift gently through these ideas, like clouds moving across a quiet sky. In a universe where time has stopped, no algorithm in the universe could halt or continue, and this reveals something fundamental about computation itself. An algorithm is a sequence of steps, a procedure for solving a problem or performing a calculation. You start with some input, perform operation after operation, and eventually, if all goes well, you arrive at an output and the algorithm halts. Or sometimes algorithms run forever, generating an infinite sequence of results. Either way, algorithms are inherently temporal. They're about doing one thing, then another, then another. Step follows step in sequence. In computer science, we even define the running time of an algorithm as how many steps it takes to complete. But steps require time. One operation must finish before the next begins. In frozen time, an algorithm caught mid-execution would be frozen at whatever step it had reached. The next instruction would never execute. The current calculation would never complete. If the algorithm was about to halt, about to output its final result, it would remain forever on the verge of halting, never quite finishing. If it was in an infinite loop, it would be frozen at one iteration, never progressing to the next. And of course, new algorithms could never begin because beginning is a process, an initialization that happens over time. The universe would be filled with frozen computations, partial calculations suspended in mid-thought, problems half-solved, outputs never delivered. Every computer, every processor, every neural network, whether made of silicon or neurons or abstract mathematics, would be locked in a single computational state, unable to progress or halt or do anything at all. And this computational freeze has a profound implication. The universe could not be simulated, neither by itself nor by anything else. There's a fascinating idea in physics and philosophy that our universe might be a simulation running on some vast computer in a higher reality. Whether that's true or not, we know that, in principle, physical systems can simulate other physical systems. A computer can run a weather simulation, calculating how air molecules move and clouds form. A quantum computer might simulate a quantum system. The universe itself, in a sense, simulates itself, each part evolving according to physical laws in a way that's equivalent to a computation. But simulation requires time. The simulating system must step through its calculations, updating its representation of the simulated system moment by moment. In frozen time, no updates can occur. A computer running a universe simulation would be frozen mid-time step. The simulated universe would never advance to its next state. And if our universe is itself a simulation, the computer running it would need time to operate, time in some external reality beyond our frozen one. More fundamentally, the universe can't even simulate itself anymore. Physical evolution, the way the universe naturally progresses from one state to the next according to physical laws, is a kind of self-simulation, reality computing its own future. But with time frozen, there is no future to compute, no evolution to simulate. The universe would be a simulation that's been paused, a calculation interrupted, a process that can neither continue nor terminate. In this frozen state, Kolmogorov complexity would be frozen as well, though it's a subtle kind of freezing. Kolmogorov complexity is a measure of how much information is in something, defined as the length of the shortest computer program that could generate it. A string of random numbers has high Kolmogorov complexity because there's no pattern, no shortcut. The shortest program is basically just the string itself. A string with a pattern, like a million ones in a row, has low complexity because you can write a short program that says print 1 a million times. This is a beautiful way to formalize the intuitive notion of information content. But notice that it's defined in terms of programs running, generating output, and programs require time to run. In frozen time, you couldn't actually run the program to verify that it generates the desired output. The Kolmogorov complexity would still exist as a mathematical property, the shortest program still exists in some abstract sense, but you couldn't execute it, couldn't use it to actually generate anything. The complexity would be a frozen number, a measure of compressibility that can never be realized through actual compression or generation. Information content would be locked into whatever state the universe had achieved, describable but not computable, meaningful but not operational. And speaking of information, no error correction could exist in this timeless void. Error correction is how information stays reliable in the face of noise and disturbance. Your computer's memory uses error-correcting codes to fix bit flips caused by cosmic rays or electrical noise. Quantum computers need quantum error correction to protect fragile quantum states from decoherence. Even DNA has error correction mechanisms, molecular machinery that checks for and fixes mutations. All of these systems work by detecting errors and actively correcting them, processes that unfold over time. The error-correcting code detects that something's wrong, calculates what the correct value should be. It flips the corrupted bit back to the correct state. This takes multiple steps, multiple operations happening in sequence. In frozen time, Errors that occurred just before time stopped would remain uncorrected. Bits that flipped would stay flipped. Quantum states that decohered would stay decohered. DNA mutations would remain unfixed. But more deeply, no new errors could occur either, because errors are changes and change requires time. The frozen universe would be locked in whatever state of correctness or corruption it had when time stopped, with no possibility of degradation but also no possibility of repair. Information would be frozen in its current state of integrity, neither improving nor degrading, just existing as it is. This frozen information landscape would also mean no scale hierarchy could form or evolve in the universe. A scale hierarchy is the idea that reality has structure at different scales, from quarks to atoms to molecules to cells to organisms to ecosystems to planets to galaxies, each level built from the previous one, each level with its own emergent properties and behaviors. These hierarchies form over time. The early universe was almost uniform, just a plasma of elementary particles. As it expanded and cooled, over time, particles combined into atoms, atoms into molecules, molecules into larger structures. Stars formed and created heavier elements. Planets formed and developed complex chemistry. Life emerged and evolved into ecosystems. Each level of the hierarchy required the previous level to stabilize, and each level took time to develop. In frozen time, the hierarchy that had already formed would remain, but it couldn't extend or modify itself. New levels couldn't emerge. Existing levels couldn't reorganize. You'd have atoms and molecules and cells and organisms, all the structure that had accumulated over billions of years of cosmic evolution, but it would be a frozen structure, unable to develop further, unable to give rise to new emergent phenomena. The scale hierarchy would be a ladder you can see but cannot climb, levels of organization that exist but cannot interact or evolve. Similarly, the universe could not be coarse-grained, and this is about how we understand complex systems by zooming out and ignoring details. Coarse-graining is when you take a system with many microscopic details and derive a simpler description that captures the macroscopic behavior. You don't track every air molecule to understand weather. You use coarse-grained variables like temperature and pressure and wind velocity that average over many molecules. You don't track every atom in a metal to understand its properties. You use bulk descriptions like density and conductivity. This works because the microscopic details average out over time. Fast molecular motions average to slow macroscopic changes. Random fluctuations cancel out to produce predictable bulk behavior. But this averaging requires time. You have to watch the system evolve, see how the microscopic details fluctuate and average. In frozen time, there's no averaging, no fluctuation, no evolution to observe. The microscopic state is frozen, and you can't derive macroscopic descriptions from it because you can't watch it evolve. The universe would be stuck at full microscopic resolution, every particle in a definite state, but with no way to coarse-grain to the simpler descriptions we use to make sense of complexity. It would be like having a photograph at infinite resolution but no ability to zoom out, to see the big picture, to understand the forest instead of just the trees. This inability to coarse-grain connects to something more fundamental. No boundary conditions could be enforced in any dynamic sense. Boundary conditions in physics are constraints on how systems behave at their edges or at specific times. You might specify that a vibrating string is fixed at both ends, or that a gas is contained in a box with rigid walls, or that the universe started in a particular initial state at the Big Bang. These boundary conditions determine how the system evolves. The fixed ends of the string determine what wave patterns can exist. The walls of the box determine how gas molecules bounce. The initial conditions of the universe determine its subsequent history. But enforcing boundary conditions often requires ongoing interaction. The wall of a box enforces its boundary condition by continuously bouncing molecules that hit it. A thermostat enforces a temperature boundary condition by adding or removing heat over time. In frozen time, no such enforcement can occur. If a molecule was heading toward a wall, it would freeze before hitting it, and the wall couldn't bounce it back. The boundary condition would be violated, or rather, the concept of enforcing it would become meaningless. Boundary conditions that were already satisfied would remain satisfied, but only statically, not through any active enforcement mechanism. The universe would be a system with constraints but no ability to maintain or enforce those constraints. At the level of fundamental physics, no field interactions could complete their processes. Fields in physics, electromagnetic fields, gravitational fields, quantum fields, interact with each other and with particles. An electron creates an electromagnetic field, and that field exerts forces on other charges. Quarks are bound together by the strong force field. The Higgs field gives particles mass through their interaction with it. All of these interactions are mediated by processes that take time. An electron emits a virtual photon, which travels to another electron and is absorbed, transferring momentum and creating a force. This happens over a tiny interval of time, but it's still an interval, a duration however brief. In frozen time, field interactions would be caught mid-process. Virtual particles mediating forces would be frozen in transit. The electromagnetic field of an electron would be frozen in its current configuration, unable to propagate changes to influence distant charges. Field values themselves would be locked, unable to respond to the presence of sources or charges. The intricate dance of fields and particles, the continuous give and take of energy and momentum through field interactions, would become a frozen tableau. Forces would exist as field configurations but couldn't do work, couldn't cause changes, couldn't complete the interactions they were in the middle of. This frozen interaction state would make thermodynamic potentials lose meaning entirely. Thermodynamic potentials like free energy, enthalpy, and chemical potential are quantities that tell you which way a system will evolve. Water flows downhill because that lowers gravitational potential energy. Chemical reactions proceed in the direction that lowers free energy. Heat flows from hot to cold to maximize entropy. These potentials are like landscapes, and systems naturally roll downhill in these landscapes, seeking minimum energy or maximum entropy. But rolling downhill requires motion, and motion requires time. In frozen time, a system might be at a high point in its free energy landscape, far from equilibrium, poised to relax to a lower energy state. But it can't roll down, can't evolve toward equilibrium. The potential exists, the landscape is still there mathematically, but the system can't traverse it. Thermodynamic potentials would become purely descriptive, telling you about the frozen state's relationship to hypothetical other states, but not predictive, not able to tell you where the system will go because it's not going anywhere. They'd be maps of a terrain that can never be traveled, guides to journeys that cannot be taken, and ultimately, all of this adds up to something deeply troubling. The universe would fail the definition of a system in the way we normally understand systems. A system in physics is a collection of interacting parts that evolves over time. The parts might be particles, fields, subsystems, whatever, but they interact according to rules, and these interactions cause the system to change from one state to another. The solar system is a system. Planets interacting gravitationally, orbiting the sun, evolving through time. A gas is a system. Molecules colliding, exchanging energy, evolving toward equilibrium. Even the entire universe is a system. Matter and energy and space-time interacting, evolving according to the laws of physics. But interaction requires time. Evolution requires time. Without time, you have parts, you have relationships between parts, but you don't have interaction in the dynamic sense, and you don't have evolution. The universe would be more like a structure than a system, a static arrangement of components that have relationships but don't interact, that have properties but don't evolve. It would fail to be a system because systems are fundamentally about change and process, and in frozen time, There is no change and no process, only static being. Now, as you sink deeper into tranquility, your body heavy and relaxed, let's explore perhaps the most philosophical implications of frozen time. What happens to meaning itself, to language, to our ability to explain and understand? Breathe slowly, naturally, and drift with me through these contemplations. In a universe where time has stopped, initial conditions become meaningless, losing the significance they normally have in physics. Initial conditions are the starting state of a system, the positions and velocities of all the particles at some chosen beginning time, the values of all the fields at that initial moment. If you know the initial conditions and the laws of physics, you can in principle calculate what will happen next, how the system will evolve. Initial conditions are crucial. Change them slightly and you might get a completely different outcome. The butterfly effect in chaos theory shows how sensitive systems can be to their initial state. But notice the temporal language here: initial, starting, beginning. These concepts only make sense when there's a progression through time. Initial conditions are what you start from before the system evolves. In frozen time, there's no before, no evolution to predict or explain. The frozen state just is. You could call it an initial condition if you imagine time restarting, but it wouldn't be initial to anything that actually happens. It would be more accurate to call it the only condition, the sole state, neither initial nor final but simply eternal. The distinction between initial conditions and later states collapses because there are no later states. Everything is simultaneous, or perhaps better to say, nothing is temporal at all. This collapse leads to something even stranger. The universe could not distinguish laws from initial conditions, and this blurs a fundamental distinction in physics. Laws of physics are universal rules that govern how things change. Newton's laws, Maxwell's equations, the Schrödinger equation. These hold everywhere and everywhen. Initial conditions, on the other hand, are specific facts about a particular system at a particular time. The laws tell you how things evolve. The initial conditions tell you what they evolve from. Together, laws plus initial conditions determine the future. But this distinction requires time. Laws are about change over time. They're differential equations, relationships between a system at one moment and the system an instant later. Without time, without change, laws have nothing to govern. They become purely descriptive, mathematical relationships between quantities that happen to be true of the frozen state. But those same relationships could be viewed as constraints on the initial conditions, requirements that the frozen state must satisfy. There's no way to distinguish this is a law that governs evolution from this is a constraint that the initial conditions happen to satisfy. The frozen universe would be a configuration of matter and fields that satisfies certain mathematical relationships, but you couldn't say which relationships are laws and which are just facts about this particular frozen state. The deep distinction between dynamical laws and contingent initial conditions would evaporate. And without dynamics, without change, no conservation laws could be verified through observation. Conservation laws are some of the most fundamental principles in physics. Energy is conserved, never created or destroyed, only transformed. Momentum is conserved in isolated systems. Angular momentum is conserved. Electric charge is conserved. These laws are profound and beautiful, connected through Noether's theorem to symmetries of nature. But we verify them by watching systems evolve and checking that the conserved quantity stays constant. A collision happens and we measure the total momentum before and after and confirm it's the same. Energy transforms from kinetic to potential and back, but the total remains constant. This verification requires time, requires before and after, requires the ability to measure the quantity at different moments and compare. In frozen time, you'd have a single frozen value of energy, momentum, charge, but you couldn't verify that it's conserved because conservation is about remaining constant over time. You couldn't watch energy transform or momentum transfer or charge move. The conservation laws might still be true in some abstract sense, mathematical properties of the frozen state, but they'd be unverifiable, untestable, purely theoretical claims about how things would behave if time were flowing but with no way to check. Conservation would become an invisible property, neither confirmed nor violated, just irrelevant. This frozen reality would also have profound implications for language itself. No reference to change could exist in language, and this would make most of our words meaningless. Language is full of verbs, words that describe actions, processes, changes. Run, grow, think, fall, burn, love, create, destroy. All of these presuppose time, presuppose that things can be different at different moments. Even static-seeming verbs like is or exists have temporal implications, suggesting ongoing being through time. In a frozen universe, you couldn't accurately use any verb because verbs describe change or states that persist through time, and neither is possible. Adjectives that describe processes would fail too. Alive implies metabolic processes. Hot implies molecular motion. Moving implies changing position. Almost every word in our vocabulary is built on the assumption that time flows, that things change, that there's a difference between now and later. In frozen time, language would become disconnected from reality. You couldn't describe what's happening because nothing is happening. You couldn't tell stories because stories require sequence. You couldn't give explanations because explanations trace causes to effects through time. Language would be like a tool designed for a world that no longer exists, full of concepts and distinctions that have lost their reference. Silent words for a silent universe. Even the concepts of fast and slow would disappear. No scale of fast or slow could exist in timeless reality. Speed is distance divided by time. Something is fast if it covers a lot of distance in a little time, slow if it covers little distance in much time. These are relative concepts, meaningful only in comparison. A cheetah is fast compared to a human but slow compared to a jet plane. Light is the fastest thing there is, the cosmic speed limit. But in frozen time, nothing moves, so nothing has speed, so the concepts of fast and slow become undefined. You might say an object was moving fast when time stopped, that it had high velocity in that last moment. But velocity is rate of change of position, and without time flowing, position doesn't change, so calling it a velocity seems wrong. It's more like a frozen direction and magnitude, a vector property of the object, but not a speed in the sense of motion. The entire scale from infinitely slow to maximally fast would collapse to a single point. No motion at all. All speeds would be zero, or perhaps better to say, the concept of speed would cease to apply. Fast and slow would join the long list of temporal concepts that have lost their meaning. This connects to another fundamental loss. The concept of equilibrium disappears entirely. Equilibrium is a state where things have stopped changing, where all the forces balance, where the system has settled into a stable configuration. A ball at the bottom of a valley is in mechanical equilibrium. A gas where temperature is uniform throughout is in thermal equilibrium. A chemical reaction where the forward and reverse rates are equal is in chemical equilibrium. But equilibrium is defined in contrast to non-equilibrium. It's meaningful to say a system is in equilibrium because it could have been changing but isn't, because it reached this state through some relaxation process over time. In frozen time, everything is frozen, so in a sense everything is static like equilibrium would be, but nothing reached that state through relaxation, nothing could change if it wanted to. The distinction between equilibrium and non-equilibrium collapses. Is the frozen universe in equilibrium? It's not changing, but it's not in equilibrium either because equilibrium implies it could change if perturbed but chooses not to, and in frozen time nothing can change whether perturbed or not. Equilibrium as a concept requires the possibility of change, requires dynamics that could occur but happen to cancel out. Without that possibility, the concept loses coherence. And without change, without dynamics, no emergence could occur. No new properties could arise from complexity. Emergence is one of the most fascinating phenomena in nature. Simple rules at one level give rise to complex behavior at higher levels. Atoms obeying quantum mechanics combine to create molecules with emergent chemical properties. Neurons following simple firing rules create emergent consciousness. Simple interactions between birds in a flock create emergent flocking behavior. Water molecules create emergent properties like waves and turbulence and phase transitions. Emergence requires interaction over time. The lower-level components must interact repeatedly, their behaviors combining and interfering and creating patterns that only exist at larger scales or longer timescales. In frozen time, the components that would interact are frozen. Neurons can't fire repeatedly to create thought. Water molecules can't collide to create waves. The substrate for emergence exists, all the components are there, but the process of emergence can't occur. Any emergent properties that already existed would be frozen in place, but new emergence would be impossible. The universe would be locked at whatever level of emergent complexity it had achieved, unable to generate new levels, new properties, new phenomena arising from collective behavior. Emergence requires time to emerge, and without time, it simply stops mid-emergence. This frozen complexity makes cosmic fine-tuning become meaningless as an explanatory concept. Fine-tuning is the observation that many physical constants and conditions seem precisely calibrated to allow complex structures like stars, planets, and life. If the strength of gravity were slightly different, stars couldn't form. If the mass of the electron were different, atoms couldn't exist as we know them. This apparent fine-tuning demands explanation. Maybe there's a multiverse with different constants in different regions, and we're in one of the rare regions that allows life. Maybe there's some deeper principle that constrains the constants. But fine-tuning is about how the initial conditions and constants affect the subsequent evolution of the universe. It's about whether the universe evolves to form stars or not, to create chemistry or not, to allow life or not. In frozen time, there is no evolution. The universe doesn't develop into anything. It just is frozen in whatever state it had. You couldn't say the constants are fine-tuned for life because life isn't an outcome of evolution. It's just part of the frozen state. Some regions of the frozen universe contain living things, frozen midlife. Others don't. But this isn't the result of fine-tuning allowing life to evolve. It's just a static fact about the distribution of frozen matter. Fine-tuning loses its significance because there's no tuning, no adjustment of parameters affecting outcomes. There are just parameters and a state, with no causal connection between them requiring explanation. And without time, without evolution, the universe would have no counterfactuals, no way to talk about what would have happened if things had been different. Counterfactuals are crucial to understanding. We explain things by considering alternatives. Why did the vase break? Because it fell. If it hadn't fallen, it wouldn't have broken. Why do apples fall? Because of gravity. In a universe without gravity, they would float instead. These if-then statements, these counterfactual conditionals, depend on imagining how systems would evolve under different conditions. They require the concept of laws governing evolution, initial conditions determining starting points, and the ability to trace out different possible histories. In frozen time, none of this works. You can't meaningfully ask what would have happened if things had been different because nothing happens at all. Different initial conditions wouldn't lead to different outcomes because there are no outcomes, no evolution to different futures. The frozen state is what it is, and imagining it being different is just imagining a different frozen state. But there's no sense in which one frozen state would lead to or explain or cause another. Counterfactuals require time and causation and laws operating over time. Without these, we lose the ability to think contrafactually, to explore possibilities, to understand why things are one way rather than another. And this brings us to perhaps the most devastating loss of all. Reality would no longer support explanation in any meaningful sense. Explanation is fundamentally about showing how one thing follows from another, how causes produce effects, how general principles account for particular phenomena. Why is the sky blue? Light scatters off the atmosphere, and blue light scatters more. Why do planets orbit the sun? Gravity creates a force, and objects follow curved paths in gravitational fields. Every explanation traces a path from conditions and laws to outcomes. But this requires time. Causes must precede effects. Principles must govern evolution. Outcomes must result from prior states. In frozen time, there are no causes and effects, no evolution, no outcomes resulting from conditions. There's just a static configuration of matter and fields. You could describe it, catalog its properties, note its structure. But you couldn't explain why it is that way rather than some other way because explanation requires a temporal or causal story, a narrative of how things came to be, and narratives require time. The frozen universe would be inexplicable not because it's too complex to understand, but because the very concept of explanation presupposes a temporal unfolding that doesn't exist. It would be a universe of pure description, where you can say what is but never why, where understanding reduces to mere observation of a static state with no deeper account possible. And now, as you rest in deep tranquility, your breath barely a whisper, let's arrive at the final contemplations. The ultimate nature of a frozen reality, the most fundamental truths about a universe where time has ceased. Let these last thoughts wash over you like gentle waves as sleep approaches. In this frozen cosmos, no edge of time could be detected, and this is a strange kind of invisibility. When time stops, there should be a boundary, a last moment when things are flowing and a first moment of frozen stillness. But a boundary requires two sides, a before and after, and in frozen time there is no after. From within the frozen universe, you couldn't detect when time stopped because detection requires observation over time. There would be no experience of transition, no moment of noticing that things had changed from flowing to frozen. The edge of time would be invisible not because it's hidden, but because seeing it would require standing outside of time, observing from a perspective that has time continuing while the universe's time stops. From inside, there would just be the frozen state, eternal and unchanging, with no marker, no indication, no detectable edge showing where time ended. It would be like living in a photograph and trying to find the boundary between before the picture was taken and after. The boundary exists conceptually but not experientially. The frozen universe would have a temporal edge in the abstract sense that it exists at one moment rather than continuing through multiple moments, but this edge would be completely undetectable to anything within that universe. And in this edgeless, frozen state, physics would reduce to pure constraint satisfaction, losing its dynamical character entirely. Normally, physics is about dynamics, about how systems evolve according to laws. You solve differential equations to predict future states from current states. But constraint satisfaction is different. It's about finding configurations that satisfy certain requirements, certain relationships that must hold. Think of a jigsaw puzzle. You're not evolving anything forward in time. You're just looking for an arrangement of pieces that satisfies the constraint that edges must match. In frozen time, physics becomes like that. The universe is in some configuration, and that configuration must satisfy various mathematical relationships. The electromagnetic field must satisfy Maxwell's equations in the sense that the frozen field configuration is consistent with those equations. The distribution of matter must satisfy Einstein's field equations in the sense that the frozen spacetime curvature matches the frozen mass-energy distribution. But these aren't dynamical laws anymore. They're just constraints, requirements that the frozen state happens to satisfy. Physics becomes a vast system of simultaneous equations, all of which must be satisfied by the frozen configuration, but with no time evolution, no dynamics, no change from one solution to another. It's physics without the physics, just pure mathematical structure. This transformation is so complete that we might say the universe would not violate laws. It would exit them entirely. Violating a law means doing something the law forbids. Breaking the speed of light, creating energy from nothing, allowing momentum to disappear. These would be violations. But in frozen time, the universe doesn't violate dynamical laws. It simply ceases to be the kind of thing those laws apply to. Dynamical laws are rules about change over time. They govern how systems evolve, how states transition to other states. If there's no change, no evolution, no transitions, then the laws don't apply because they have nothing to govern. It's like a game where the rules tell you how to take turns, how to move pieces, how to win. If you freeze the game mid-play, you're not violating the rules. You're just in a state where the rules no longer apply because the game isn't being played anymore. The universe would exist outside the domain of dynamical laws, not as a violator but as something that has transcended or exited the framework those laws operate within. The laws would still exist as mathematical structures, elegant and true, but they'd be laws of a universe that no longer exists, descriptions of dynamics that no longer occur. In this strange state beyond dynamics, there would be no distinction between real and virtual states, and this blurs a line that's usually quite sharp. In quantum field theory, we distinguish between real particles that persist and can be measured, and virtual particles that exist briefly as part of quantum fluctuations or as intermediaries in interactions. An electron is real. The virtual photons that mediate electromagnetic force are virtual. Real particles are on their mass shell, satisfying the energy-momentum relation. Virtual particles can be off-shell, borrowing energy from the vacuum for brief periods allowed by Heisenberg's uncertainty principle. But this distinction requires time. Virtual particles exist for brief moments, too short to directly observe, while real particles persist. In frozen time, nothing persists because persistence requires time, but nothing is brief either for the same reason. A virtual particle caught mid-existence would be frozen there, neither brief nor persistent, neither real nor virtual in the usual sense. It exists in the frozen configuration, contributing to the frozen fields and forces, but you can't say it's virtual because virtual implies temporary. You can't say it's real because real implies it could be measured over time. The distinction collapses into irrelevance. All particles, real and virtual, become just features of the frozen state, mathematical objects in the configuration, without the temporal properties that normally distinguish them. This collapse of temporal distinctions extends to mathematics itself. Mathematical limits involving time become undefined or lose their physical meaning. In calculus and physics, we often take limits as time approaches infinity or as a time interval approaches zero. What happens to the universe as time goes to infinity? What is the instantaneous velocity, the limit of change in position as the time interval approaches zero? These limits are fundamental to how we do physics mathematically. Derivatives are limits as time intervals shrink. Integrals sum over time. Infinite time limits tell us about equilibrium states and ultimate fates. But in frozen time, these limits become problematic. You can't let time approach infinity because time isn't flowing at all. You can't take a derivative with respect to time because there's no infinitesimal time interval to consider. The mathematical machinery we use to describe physics is built on the assumption that time is a continuous parameter we can vary, approach limits in, differentiate, and integrate over. Remove that assumption, freeze time at a single value, and the machinery breaks. The limits aren't false. They're undefined, inapplicable questions about a variable that no longer varies. Mathematics would still work in describing the frozen spatial structure, but all the temporal mathematics, all the powerful tools we've developed for analyzing change and motion and evolution, would become empty formalism. And without these temporal tools, the universe could not be described dynamically, only statically, and this is a profound limitation. A dynamical description tells you how things evolve. Given the state now, here's what will happen next. Given the initial conditions, here's the trajectory through phase space. Given the Hamiltonian, here's how the quantum state evolves. This is the language of physics, the way we understand and predict and explain. But it's inherently temporal. In frozen time, you could still describe the universe statically. Here is the distribution of matter. Here are the values of all the fields. Here are the positions and momenta of all the particles. It's a complete catalog of the frozen state, potentially infinite in detail. But it's not a dynamical description. It doesn't tell you how the state came to be or where it's going because it's not going anywhere. It doesn't predict because there's no future to predict. It doesn't explain in the dynamical sense of showing how causes lead to effects. It's just a snapshot, a freeze frame, a static portrait of a universe that has lost its motion. Physics would become descriptive rather than predictive, cataloging rather than explaining, a vast database of frozen facts with no narrative, no story, no temporal flow connecting them. In this static universe, no synchronization could exist anywhere, and this eliminates something we usually take for granted. Synchronization is when different systems keep time together, when their rhythms align. Two clocks are synchronized if they show the same time. Fireflies synchronize their flashing. Particles in a laser synchronize their oscillations. Synchronization requires multiple things changing over time in a coordinated way. But in frozen time, nothing changes, so there's nothing to synchronize. You might say that, in a sense, everything is perfectly synchronized because everything is frozen at the same moment, but that's not synchronization in the meaningful sense. Synchronization is about maintaining coordination over time, about rhythms that match as they evolve. Without evolution, without rhythms, without time flowing, the concept of synchronization becomes empty. Everything would be static together, but that's not the same as being synchronized. It's more like being equally dead, equally frozen, equally timeless. The harmony that comes from synchronization, the coordination that requires active maintenance over time, would be replaced by the mere coincidence of existing at the same frozen instant, which isn't coordination at all, just simultaneity without duration. At the most abstract mathematical level, the universe becomes describable only as a manifold, and even that description is questionable. A manifold in mathematics is a space that locally looks like ordinary Euclidean space. Space-time is a four-dimensional manifold in general relativity, curved and warped by matter and energy, but still locally smooth and continuous. In frozen time, the universe might still be describable as a three-dimensional spatial manifold, a geometric structure representing the frozen configuration of space. But it wouldn't be a space-time manifold anymore because there's no time dimension. And even calling it a manifold seems incomplete because manifolds are usually considered as spaces you can move through, explore, traverse. In frozen reality, there's no motion through the manifold, no geodesics being traced, no paths being followed. It's a manifold in the purely abstract geometric sense, a mathematical object with certain topological and geometric properties, but lacking the physical interpretation that normally makes manifolds useful in physics. The manifold would be a frozen geometry, a shape without dynamics, structure without process, existing in some purely mathematical realm disconnected from the temporal reality we normally inhabit. And this raises perhaps the deepest question of all. The universe could not even be said to exist in the usual sense when time stops. What does it mean to exist? Normally, to exist is to persist through time, to be here now and still be here a moment from now, to endure, to continue. Even things that change are said to exist as long as they persist in some form. A flame exists even though it's constantly consuming fuel and releasing energy because it persists as a process. A person exists even though their atoms are constantly being replaced because they persist as an organized system over time. But in frozen time, nothing persists because persistence requires time. Nothing endures because duration requires time. The frozen universe would be at one moment, locked in a single instant, and you can't really persist through a single instant. Persistence requires at least 2 moments to persist between. So does the frozen universe exist? It has a configuration, a state, a structure, but it doesn't endure. It doesn't continue. It doesn't persist through time in the way we normally think of existence. Maybe it would be more accurate to say it subsists rather than exists, that it has being but not temporal being, presence but not duration. Or maybe the concept of existence itself is so deeply temporal that it simply doesn't apply to a frozen universe, and we need a new concept, a new word, for this strange mode of being that has structure and properties but no time. And in this timeless being, only mathematical consistency would remain as the sole organizing principle. In our flowing universe, reality is constrained by both mathematical consistency and dynamical laws. The configuration of the universe must be mathematically consistent, fields and particles satisfying appropriate equations, but it must also evolve according to dynamical laws that govern change over time. In frozen time, the second constraint disappears. Dynamical laws become irrelevant because there's no dynamics. What remains is pure mathematical consistency. The frozen configuration must be self-consistent, with all the fields and particles and forces arranged in a way that doesn't contain logical contradictions, that satisfies the mathematical relationships that would be satisfied by a valid state of the universe. But there's no requirement about how it got that way or where it would go next because there is no way and no next. Mathematical consistency becomes the only law, the only principle governing reality. The universe would be like a vast mathematical structure, a solution to an enormous system of equations, frozen in one particular solution with no dynamics to select among solutions or evolve from one to another. Pure structure, pure mathematics, pure frozen consistency. A universe that has shed everything temporal and retained only the eternal, unchanging realm of mathematical truth. Let these final thoughts drift away now like autumn leaves on still water. You've journeyed through the impossible, contemplated the unthinkable, explored a universe frozen outside of time. But you rest here, now, in flowing time, in a universe alive with change and possibility. Each breath carries you forward through moments that follow one another in beautiful sequence. Sleep comes like the gentlest sunset, time flowing you into dreams, into rest, into the peace of a cosmos where time carries all things gently onward. Sleep now in time's sweet embrace.